The duration of a bond is an important measure that helps us to understand the interest rate risk of a bond. In this lesson, we look at the first measure, Macaulay duration. Let's begin. In the last lesson, we illustrated that the investment horizon of an investor has a great effect on his returns in the event of changes in market interest rates. For an investor with a short horizon like Sally, the market price risk of the bond outweighs its reinvestment risk. Conversely, for an investor like Leonard with a long investment horizon, the reinvestment risk outweighs the market price risk of the bond. We have shown that for both cases, an increase in yield prior to the first coupon date would cause the market price to drop, but in the case of the investor with a long horizon, the increase in reinvestment return more than makes up for the price drop, causing the net returns to the investor to increase. In contrast, the investor with a short time horizon will have lower net returns. And the situation is opposite when interest rates decrease prior to the first coupon date. In this case, the decrease in reinvestment returns is more than the increase in market price. The net returns to the long-term investor decreases, while the net return to the short-term investor increases. As such, for an investor with a short investment horizon, her net returns will have an inverse relationship with market interest rates. Conversely, the long-term investor will have net returns that are directly related to market interest rates. So, you may be wondering, can we find this equilibrium point where the effect of a change in yield to maturity causes the change in market price and reinvestment return to just offset each other? Here we introduce the concept of duration. In particular, we shall discuss on Macaulay duration in this lesson. In essence, when a bond investor's investment horizon matches the bond's Macaulay duration, a parallel shift in the yield curve prior to the first coupon payment will minimally affect the investor's net return. So, what on earth is Macaulay duration and how do we calculate it? In general, the duration of a bond is a measure of its interest rate risk. More specifically, it measures the sensitivity of the bond's full price to a change in its yield. This means that if the duration of a bond is high, we would expect a high fluctuation in the bond's price when its yield changes. If the duration is low, the price fluctuation due to change in interest rate will be low as well. There are a number of duration measures that we will go through. The measure we're looking at now was first introduced by Frederick Macaulay, and his formulation is referred to as Macaulay duration. A bond's Macaulay duration is calculated as the weighted average of the number of years until each of the bond's promised cash flows is to be paid. The weights are the present values of each cash flow as a percentage of the bond's full value. Let's bring back our example from last lesson and calculate the Macaulay duration of the bond which Sally bought. Recall that the bond was a $1,000 par fixed coupon bond with 3 years to maturity. The coupon rate is 8% paid annually. Sally bought the bond at $1,081.70, or a yield to maturity of 5%. So to calculate the weights, we first discount each cash flow by the current yield of 5%. This is followed by dividing the figures by the full value of the bond, which is $1,081.70, and we get the following weights. Note that the present values of all the promised cash flows sum to $1,081.70, which is the full value of the bond, and the weights sum to 1. Now that we have the weights, and because we know the time until each promised payment is to be made, we can calculate the Macaulay duration for this bond, which turns out to be 2.792. Let's recap the steps to calculate the Macaulay duration of a bond. First, identify all the cash flows. Next, discount them to their present values using the yield of the bond, and divide each present value with the value of the bond to get the weights for each year. The Macaulay duration is the sum of the weights multiplied by the number of years to the payment of the cash flow. Do note that the method we've discussed is for a bond with annual cash flows. The Macaulay duration of a semi-annual coupon bond can be calculated in the same way. Each period is half a year and the discount rate is halved. In this case, the result is the number of semi-annual periods rather than years. Let's go back to our example of Sally's bond purchase. We have calculated the Macaulay duration of the bond that she purchased, which is 2.792 years. As mentioned at the beginning of the lesson, when the investment horizon of an investor just matches the Macaulay duration of the bond, the effect of a change in yield to maturity of the bond on its market price and on the reinvestment income just offset each other. This means that if the yield to maturity changes after purchase and before the first coupon, and remains at that rate till maturity, we will expect no change in the investor's return for this period. Recall from the previous lesson we had a scenario where the yield to maturity rose to 7% after Sally bought the bond. She sold the bond after 2 years, and we calculated that her realized return is 4.22%. Now, let's calculate her realized return if she sells the bond at the Macaulay duration of 2.792 years instead. Let's first calculate the market price of the bond at 7% yield at this point. There are 0.208 years to maturity, where Sally will receive the principal of $1,000 plus the last coupon of $80. If we discount this amount by 7% for this period, we get $1,064.91. Next, we calculate the reinvestment returns. The first coupon of $80 was reinvested at 7% interest for 1.792 years. We will expect $90.31 when the bond is sold. The second coupon was also reinvested at 7%, and this time for 0.792 years. We expect $84.40 when the bond is sold. Adding up the three figures, we get a total sum of $1,239.62 for an investment horizon of 2.792 years. This is based off an initial investment of $1,081.70. Annualize the figure, and we get a realized rate of return of 5%. Notice that this is the same as the yield to maturity at purchase. So, even though the yield to maturity of the bond has risen to 7% after purchase, Sally can still realize the same yield of 5% if she sells the bond at the Macaulay duration. From this example, we have learnt that if the investment horizon of the investor is equal to the bond's Macaulay duration, there should be minimal change to the investor's rate of return when the bond's yield to maturity changes. The difference between a bond's Macaulay duration and the investor's investment horizon is referred to as a duration gap. A positive duration gap exposes the investor to market price risk from increasing interest rates. So in this case, if Sally sells the bond before this day, the rate of return will be lower. A negative duration gap exposes the investor to reinvestment risk from decreasing interest rates. So if Sally sells the bond after this day, the rate of return will be higher as the coupons will have more time to earn higher interest. And that concludes this lesson, where we were introduced to Macaulay duration as a measure of a bond's sensitivity to changes in interest rates. There are, however, a number of improved measures of duration besides Macaulay duration. We shall discuss them in the coming lessons. See you again.